Assalamu alaikum. Today we are going to recap everything you've took from the very beginning, since most of you were not satisfied by last week tutorial, because obviously you have to understand entropy well to understand Exergy, and the problem is that for the last 2 semesters, I think the entropy chapter was not explained in the engineering thermos course. So I will try my best to recap for you everything that you have took before. And okay, let's start. Let's start by chapter 1. In chapter 1, you basically took you learned what's the meaning of thermodynamics, which is obviously you can describe it as the science of energy, meaning that anything related to heat or work or any form that we can transfer to energy is important for us. And then we took some basic stuff about units and this stuff. We talked about systems and how we have closed systems and open systems, and we talk about the surroundings and the boundary and how we are going to define the system, which is a place in space that we want to study. And the boundary is the edges of that system that you are studying, and you have to know this stuff, as I guess. The properties and the intensive and extensive properties, the specific properties, which are the extensive properties, the ones that do not depend on mass, when we divide them on mass. And then in the second chapter, you took the mechanical energy, which is, yeah, let me write for you, equation. Okay. In chapter 2, you've took equation like this. It's similar to Bernoulli's equation. Half rho v squared plus so on this one, v squared over 2g plus z equal to constant. Okay, this is the mechanical energy equation. Now, the mechanical energy equation is very important for us, especially in the Exergy chapter, because each term in this equation is going to fully give us work. What does that mean? Every form of the mechanical energy equation is fully convertible to work. There are no losses. So if you want to make this is the flow work, and this is the, or we can call it dynamic work, and this is the potential, or this is the kinetic energy, if we can call it also, and this is the potential energy. Each one of these forms of energy can be fully transferred to work without any losses. So we'll not lose everything. So when we include them in the Exergy equation, we are not going to have any losses, either from the flow work, from the kinetic energy, or from the potential energy. Okay, so this is the importance of what you when you took the mechanical energy equation. And then in chapter 3, you learned about the phases, okay, and how to read the tables. You have these states, which are the saturated liquid state, saturated mixture state, and the saturated vapor state, okay? And you have here 2 states beyond these 2, which are the superheated state and the subcooled state, okay? And you know how to get them from the tables. If you have a temperature here fixed and you have the pressure is less than Tsat, sorry, if they have the pressure is more than Tsat, then you are going to have a subcooled. If it's less, then you are going to have a superheated state. If you fix the pressure, then you are studying by the temperature, then it's going to be the other way around. And if you have another state, something not temperature or pressure beside them, if you have like enthalpy or entropy or maybe internal energy, then you can define if that state is in the saturated mixture region from the quality X, okay? And then in chapter 4 and 5, you took something very important, which are the closed system and open system devices. These you are going to see in every chapter, I think, from now till chapter 14. So remind me, what are some of the closed system devices that you took? The rigid tank, okay, rigid tank. and you also have the piston cylinder device, okay? In the rigid tank, what's the characteristics of the rigid tank? You have a constant volume in the rigid tank, okay? So the volume is constant, obviously, because it's a tank and it's closed, so its volume will be constant. In the piston cylinder device, you have this piston here that moves and gives a boundary work. And then the piston is controlling the contents or the pressure inside this chamber. So here we are regulating the pressure, which is constant. Okay. This is the closed devices that you took. And for the open system device, you had many ones. You had the diffuser, you had the other one, the diffuser, and you have also the what do you call it? Diffuser and nozzle, yeah, the nozzle, one which increase the velocity in exchange of pressure, and one that does the other way around. And you also had the, okay, this is the shape, and you also have the compressor, okay. You have also the turbine. You have many devices here. You have also the throttling valve, the one that keep the enthalpy constant. You have also duct. Okay, maybe you can have a heating coil inside this duct, and we have an inlet and an outlet. Many devices you had in the open system devices. Okay, chapter 6 we will come to it later when you took the cycles, because it's related to the cycles mostly. And in chapter 7, this is the important part that you didn't took it well in thermodynamics. So it's about entropy. Okay, what is the definition of entropy, or what's entropy exactly? We can't give a clear definition to entropy, but we can understand or have a sense of what is it. So in simple words, it's the randomness. Okay, the randomness. Okay, of course, we are talking about the thermodynamics entropy, because there are other definitions for entropy in other sciences. But here it's the randomness of the molecules. And why is it important for us? We know that energy, okay, starts from the molecular level of the matter. So if these molecules are random, are going in a random motion, are hitting each other, then we are going to get more energy, basically. And if these molecules are still and they do not move, then you are having less energy. So this is the importance of entropy. You are studying the entropy to know the randomness or the distortion of these molecules, so that you can have a sense of the energy that these molecules do have. Okay. Yeah. Okay. And you had this equation for the entropy balance, which is equal to the change of this entropy in the system equal to the entropy by heat, okay, or you can call it the entropy N, which can include entropy by heat or entropy by mass. And there's this important principle here, which is that the entropy generated from work is 0, okay, and minus the entropy out. But there is another term here that's called the entropy generated. Okay, this term is related to the reversibilities. If our system is totally reversible, then we are not going to have this term. The reversibilities are, in simple terms, are just the losses. So if we're having any interaction that can have losses, like heat transfer can have losses. So then we will have the entropy generated. If you don't have things like that, just mass in and mass out, then we will not have any entropy generated from our system. Okay, and the rest is just equations. So the entropy by heat is the heat over the temperature of the boundary. The entropy by mass is m dot times s small, and that's it, basically. So let's try to solve some some problems about the entropy and to get the hang of it, and then we can go and start with the Exergy chapter. Okay. To start with, we will take some simple problems, the ones that are already solved in the examples. Okay. Okay. So we're having a piston cylinder device that contains a liquid vapor mixture of water at 300 Kelvin. During a constant pressure process, 750 kilojoules of heat is transferred to the water. As a result, part of the liquid in the cylinder vaporizes. Determine the entropy change of the water during this process. Okay, so we want just to calculate the entropy change of water in this simple process. We don't have any mass in or mass out because obviously it's a closed system. Okay, and we don't have work, and even if we have work, doesn't matter in the entropy because we don't have entropy coming from work. Okay, so the only things that produce entropy are the heat and the mass, remember them. So we only have this amount of heat that's transferred to the water, and we have the temperature of the boundary. Then the change of the entropy will be Q over temperature of the boundary, which is the same as the temperature of this system because it's at a constant temperature. Then 750 kilojoules over 300 kelvins will give us the change of entropy of that system. Okay, this is a very simple one. Okay, this one is somehow also related to it, just substitution of the equation of Q over T for the entropy coming from heat. Okay, we have a heat source at 800 Kelvin that loses 2000 kilojoules of heat at a sink, and 500 Kelvin. Okay, this is the temperature of the sink, and this is the other temperature of the sink. So we have two temperatures for two different sinks. This is case A, and this is case B. Okay, a heat source can be like a furnace or a boiler or anything, and this is the heat sinks where it's basically rejecting the heat that's coming from the source. So we want to know which heat transfer process is more irreversible. You know, how can we define the irreversibility? The irreversibility was coming from this term that I talked about, the entropy generated. Okay, this is the entropy generated term.
But yes. Isn't there any difference between irreversibility and randomness?
Irreversibilities and randomness. Now, the randomness or the motion of the molecules is related to the entropy, and then if we have reversibilities, they are part of the entropy, but they are not like the whole thing. They are just some of it. You got me? Or so the irreversibilities are these losses in the heat transfer problem that you have that are causing more distortion or more randomness in the molecules, but they are not the whole or the total case of the randomness that's in our system. So that randomness can come from other things. Maybe we have mass n, or maybe you have from mass. So the other form of
so irreversibility is a part of entropy that causes exergy destruction, right?
Yes, yeah, that's right. Yeah. Okay, that's related to the principle of Exergy destruction with the entropy, but now I'm just like talking about the entropy. I will later go to the principle of Exergy destruction. So determine which heat transfer problem is more irreversible. We can do that by just calculating the entropy generated. How we can calculate the entropy generated? Just grab this equation. Okay. What forms of entropy in we have, what forms of entropy out we have, and what is the change of the system. All of this depends on how do you define your system. Okay. I'll prefer in a problem like this to do your system as that here. Enclose your system like that. So put the source and the sink inside your system. then you will not have any form of losses, okay, from your system. So this 2000 kilojoules of heat that was lost will not be lost from your system. It's inside, okay? So it's an internal interaction, okay, here. The same thing for this second system. Look how it goes, okay? So okay, the change of the system equal to, we don't have anything, any entropy in, we don't have any entropy out, we just have the entropy generated, okay? Because we have heat transfer. It's not from the system, outside of the system or inside of the system, but it's in the boundaries of the system. Still, this will cause entropy generated, okay? Because there is heat transfer. It's not to the outside or inside, but it's inside of the system. So the irreversibilities are happening inside of that system, okay? So how can we calculate this change in the system? Our system composes of two parts, the sink and the source, okay? So we have the change of entropy for the sink and the change of entropy for the source, okay? Then for the sink alone, we will have Q over T, and for the source alone, we will have Q over T, because there is no mass that's crossing the sink or the source, just heat crossing the sink and the source, not the system. The system encloses both of them, okay? So for the sink, the heat will be in or out or out. Look at it. For the sink, the heat will be in, okay? So it's going to the boundary of the system. And for the source, the heat will be out, okay? So here the heat will be negative and here the heat will be positive, okay? So negative for the source and positive for the sink. And it's the same amount of heat, 2000 kilojoules, 2000 kilojoules, with different temperatures, of course. Now compare between those two systems with different sinks, the one with the 500 Kelvin sink and the one with the 750 Kelvin sink. Which one have more entropy generated will be the one with the more irreversibilities, okay? We can know that without calculating, because this is a heat transfer problem, okay? And the temperature is going from 800 Kelvin to 500 Kelvin. There is a way more ways for the losses to happen, okay, from 800 to 500 kelvins, other than if you have like from 800 to 750. And if you have this at 800, then you will not have any heat transfer, which means like you have zero losses now in this case. So when we are having like a bigger gap in the between the temperature of the source and the temperature of the sink, we can expect, of course, more irreversibilities to happen and more entropy generated to we can get from our problem, okay? But we just wanted to do it in the equation so that you get the hang of it, okay? These are very easy. They are just, there is no mass, there is nothing, just heat, okay? And you have only one system. It encloses both, everything, so you don't have entropy in, entropy out, just the generated entropy. Do you have any question till now? Okay. Yeah. Now we're having some systems, okay? We have a rigid tank that contains 5 kilograms of refrigerant 134A. And this refrigerant is initially at 20 Celsius, okay? 20 degrees Celsius and 140 kilopascals. The refrigerant is now cooled while being stirred until its pressure dropped to 100 kilopascals. Determine the entropy change of the refrigerant during this process. So we want to know the entropy change of the refrigerant in this process. of course, we will always resort to our entropy balance equation. And remember, entropy is not like energy, so it's not conserved, okay? And it can be created or destroyed, okay? Or let's say can be created from the entropy generated. Entropy generated means like that you are now creating some entropy that's not transferring from another source. In the energy equation, you had the change of the energy of the system, okay? And then the energy in minus the energy out. So we are not creating any energy, and we are not destroying any energy. If there is any energy lost from your system, then it's going to be lost to the surroundings, to anywhere else, but it's just changing its form, okay? And also there is no energy that's going to be destructed. But in the entropy balance, okay, or in the entropy, we have entropy in minus entropy out plus the generated term. Generated term is an entropy that's created. And we said from where it's created from the irreversibilities, okay? And later on in the Exergy equation, we will have Exergy in minus Exergy out minus Exergy destroyed, which means that Exergy can be destroyed. So this is the difference between the energy and the entropy and the Exergy, okay? In the sense of equation and the sense of the definition. Okay, so let's continue.
Can we prevent the destruction of Exergy?
Can we prevent the destruction of Exergy?
Yes.
So you don't want to have any Exergy destructed. Yeah, if you don't have any reversibilities in your system, or if you have forms of work that can be fully transferred or forms of energy that can be fully transferred to work, like the mechanical energy I talked about in chapter 2. Mechanical energy can be fully transferred to work. You will not have any losses, okay? If you have any other form of work, then that work will not all be useful. We will, when we talk about the definition of Exergy, we'll come to it. The Exergy is translated to the availability, okay? Availability. This means that from the state that I have, or from the energies or the works that I have, what are the maximum that I can produce, okay? This is called the Exergy, the availability, okay? This is like a better definition for it, the availability. And if you don't want any Exergy destructed, so you want to use all the energy that you have here in your system, you want it all to be useful, okay? Of course, that's not possible because, let me draw here a pie chart for you. Let's say that this is the total energy, okay? Now, there is a part of energy that cannot be used. This is not called the Exergy destructed. This one, it cannot be used by nature, okay? Maybe for limitations of that form of energy or something, this one cannot be used. And then you have, this is the amount that can be used. If all of this amount that can be used is transferred to work, okay, or transferred to energy, then you don't have any Exergy destructed. But if you have some Exergy destructed, then you are going to lose some of this amount eventually, okay? So to prevent the Exergy destruction, either you have a system that works fully on mechanical energy so that it transfers fully to work, okay, and you don't have any Exergy destruction, okay, yeah, that's basically if you don't have any Exergy destruction. And also don't have a system that includes heat transfer. Obviously, you know that heat is not a part of the mechanical energy, okay? So that's if you have a system that fully operates on mechanical energy, let's say maybe a shaft that rotates by a flow that's passing through it, then you don't have any Exergy destruction. We'll come to it. I will. There's also like simple problems involved in Exergy. Yeah. Yeah. So if you have like mechanical energy, then this mechanical energy or this kinetic energy, which is a form of the mechanical energy, will all be transferred to work, which is the same as the exergy. So here you just put equal to x. Okay, this amount of kinetic energy is the exergy that you have. Okay, and this is the chart that I told you about. This is the total energy, and this is the exergy, which is the useful part, and this is the unavailable energy, the one that cannot be used in nature. Okay, then if you don't have any losses from this one, then you don't have any exergy destructed. If you have some losses, maybe because you have other forms of work other than the mechanical energy, or if you have heat transfer or any type of other irreversibilities, then you are going to have some exergy destructed. Okay. So this is the difference between entropy and exergy. Entropy does not relate that much to work, but exergy is deeply involved in the work. When you reach that part, you are going to deal with the three equations. So that's why it's important that you know everything that you've took so far, because some problems in the exergy require you solving the problem from the beginning to the start, and you have like some three unknowns. So you're going to solve the first unknown from the energy equation, the second unknown from the entropy equation, and then you go to the exergy equation. Okay, not all problems, but some of them have this technique of solving. Okay, let's go back. Sorry guys if some of you feel like this is a bit of boring, but or for those of who maybe took entropy in thermodynamics, but I guess most of you didn't, so we are doing this part. Okay, now determine the entropy change of the refrigerant during this process. Okay, yeah, now the change of entropy of the system, this is a closed system, equal to the entropy in minus the entropy out plus the entropy generated. Okay. Will we have any entropy generated in this process? Let us see. There is some kind of heat transfer. Okay, the refrigerant is now cooled while being stirred until the pressure drops to 100 kilopascals. So you have some heat losses. Then you are going to have entropy generated. But you don't need to solve the problem from this side. You just want to solve it from this side because he is asking you for the change of entropy in the system. If you have everything in this side, then no need to go to this side because there is an unknown here. Okay. Maybe you have the entropy and you have the entropy out, but you don't have the generated part. Okay. So the change of the entropy in the system is okay. S1 minus S2 or S2 minus S1. What was the first state? It's a refrigerant. So you grab the tables A12, A11, A12, A13 that you have. Okay, and see what state do you have at state 1. This is from chapter 3. And what state do you have at state 2? Okay, and then from that you can get the small s, okay, the specific entropy, and then you can say like our change of the system is equal to the mass multiplied by the specific entropy of state 2 minus the specific entropy of state 1. Of course, you can make it 1 minus 2 or 2 minus 1, depending on what change you are calculating. Are you calculating like how was it and then how did it got to, or in the reversed order? It's just like be consistent. Okay. So at state 1, we have the pressure and the temperature. The entropy can be got from table A11. If we go, please keep the tables in front of you so that you can follow. I will try to open the tables to okay, it's locked off. Okay, we can open it from here. Bookmarks. Okay. Remember, we had like 20 and 140 kilopascals, yeah? So 20 Celsius, 140 kilopascals. Obviously, we have the pressure is lower or higher than PSAT. It's lower than PSAT. So if our pressure is lower than PSAT and we are fixing the temperature, then we know that the state will be superheated, yeah? Because the pressure is lower. So we need to go to table A13. We go to the pressure that we have, the temperature that we have, and then we can get this specific entropy, okay? This is, I guess, 1.0625. Okay, so let's go to the problem. Yeah. And then for state 2, we have the pressure, but we don't have anything else. Just the problem tells us that its pressure dropped until it became at 100 kilopascal. But what other information we have? We have that this is a rigid tank system, a closed system of a rigid tank type. And in a rigid tank, we have the volume is fixed. And when the volume is fixed, you can use this information to know the state at 2. Okay, so get the volume, and now fix the volume, because obviously you have a rigid tank, and then you can get the properties. Okay, turned out to be a mixture, because it's between the VF and VG. So now you can calculate X and therefore calculate the S2. The mass of this system can be either given, or maybe you are asked to calculate it if you have not a water system or refrigerant system, but maybe if you have a gas system, then you can calculate the mass from the ideal gas equation. Okay, then that's the change of the entropy of your system. I think it's simple. Do you get it? And obviously we didn't account for the shaft work because there is no entropy generated from work. Okay. The same thing will be applied to open systems. So this is an open system problem that we have. We have a steam turbine, and then we are asked to calculate the output work of the turbine per unit mass steam. Okay. Obviously, we cannot get the work directly from the entropy equation because there is no work in the entropy equation, only heats and masses. But what can we do in this problem? We know here from the statement that the steam enters an adiabatic turbine at 5 megapascals and 450 Celsius and leaves at a pressure of 1.4 megapascals. Determine the work output of the turbine per unit mass of steam if the process is reversible. When you see that the process is reversible and adiabatic at the same time, then it's isentropic. Why? If it's reversible, then this means that you don't have any entropy generated. And if it's adiabatic, then this means that you don't have any heat interaction. Yeah, or yeah. Okay, so this is your system. Okay, when it's reversible, this means that you don't have any entropy generated. Okay, and when it's adiabatic, this means that you don't have any heat interaction, nor in nor out. I know that if you have heat, by definition, you are going to get entropy generated. But if you have these both statements, then it's assuring you that you do have an isentropic problem. Okay, you will have the change of the entropy of the system to be equal to 0. Okay, when the problem says that it's reversible and adiabatic at the same time. So from this, what you can get, you can say that S1 is equal to S2, and then use this to solve in the energy equations. See how everything connects? You have the state here, P1 and T1. You have here P2, but you don't have anything else. And it's not a rigid tank, it's not a piston cylinder, so you can't fix the pressure or the volume. So it's giving you this hidden information in the problem, that the steam turbine is adiabatic and the process is reversible. So it's an isentropic process, and therefore I can calculate the entropy at the inlet and fix it with the entropy at the outlet to know the state at 2. And if I know the state at 2, then I can calculate the work out using the energy equation, not the entropy equation. You can use the Exergy equation to get this one, but like you're going to complicate it on yourself. The energy equation is easier. Okay. Just its direct substitution will be at the end. Okay. If you have S2, then you have H. You know that in open systems we go for H, not for U, when we are dealing with the energy. Then the difference in the H's is going to be the work out per unit mass. If you have the mass, you can multiply it with it to get the amount of work that's actually produced by the steam turbine. Okay, I think we finished everything that's related to entropy, but there is also one small thing that I want to talk about, which is here. Yeah. When you have system of a gas, or like mainly air, because we have tables for air. Okay, so in this case, if you have an air compressed by an adiabatic compressor, so this compressor is adiabatic, from 100 kilopascals to 12 Celsius to a pressure of 800 kilopascals at a steady rate of 0.2 kilograms per second. So he's giving us the flow rate. If the isentropic efficiency, okay, this is what's called the isentropic efficiency, and it determines how isentropic is this compressor. So if the isentropic efficiency is 100%, then your compressor is isentropic, meaning that it operates at a constant entropy. Okay, see here in the TS diagram, this is state 1, and if your compressor is totally isentropic, then it will go from here to here, just raising the temperature and keeping the entropy constant. But obviously, in the actual operation, it will have some deviation from that constant entropy line that you have here. This deviation is accounted for, in what's called the isentropic efficiency. So he is giving you that the isentropic efficiency of the compressor is 80%. Determine the exit temperature of the air and the required power input to the compressor. So this isentropic efficiency that's accounted for in this deviation, have a small equation here, the isentropic efficiency of a compressor, and we have also the isentropic efficiency of the turbine, and I think also we have an isentropic efficiency for a nozzle, but this is not used a lot. So how does it go? In a compressor is a work-consuming device, not a work-producing device. So for a work-consuming device, we expect the isentropic, before I begin, we expect the isentropic process to have the maximum amount of power output and the minimum amount of power input. So if we have a process that's isentropic, this is the most ideal case that we have. So if we are generating power, then we are generating the most power that is possible. And if we are taking power or consuming power, then we are consuming the least amount of power that's possible. So for a compressor here, okay, the isentropic efficiency, of course, it have to be 100 or less. Then the amount of work, okay, that is consumed, okay, that's consumed in a non-isentropic compressor, so we will call it an actual compressor or an actual work. And here we have the amount of work that is consumed from an isentropic compressor here, S. This one obviously have to be always less than this one or equal to it. When they are equal, it's going to be 100%. And in the normal case, of course, it's going to be less than it. So now you know the equation, okay? For a turbine, it's the other way around. We want to produce maximum work. So the isentropic work is going to be maximum always, and the actual one is going to be approaching it till we reach the isentropic state, which is when we have the maximum production of work from that turbine. Okay. So this is another benefit from analyzing the entropy that we are measuring the irreversibility, and we also have a sense from the entropy in which we can measure the performance of devices, mainly the compressor and the turbine. Okay. So this is a compressor. So the equation for the this is the equation that we are going to use, and of course it's going to translate to H2 minus H1, H2 minus H1. Okay, the first state, it's going to always be the same. The change will be in the second state. Okay, as we saw here in the TS diagram. Okay, this is the first state, and this is the isentropic process, which is 100% isentropic efficiency, and here's the deviated process, or the actual process, that like it's less than 100. Okay, isentropic efficiency. So the state 1 will always start from the same point. Now this is H1, this is H1 here, H2S for the isentropic case, H2A for the actual case. Okay. For the isentropic case, it's easy to obtain it because we just fix the entropy. Okay. Here we have temperature 1, okay, and pressure 1. Remember, for air, you go to table A17. We have it after the refrigeration tables. So if we go to table A17, we can find the properties of air, and we can get the enthalpy at that state. Remember, for gases, the enthalpy is only a function, or for ideal gases, the enthalpy is only a function of temperature. So you don't even need the pressure here. Okay, you need it for something else, but you don't need it to calculate the enthalpy. Okay, so now we have the enthalpy here. And for the isentropic case, we can just fix the entropy. But how can we get the entropy here? We don't have calculated numbers for the entropy of air, unlike water and refrigerant. So when we have an isentropic process, we are going to use the pressure ratio relationships. Okay, you are going to go back to it in the cycles chapters also, chapter 9. But for the pressure ratio relationships, you are going to get this relative pressure from the tables that corresponds to T1. You can find it in the air tables, as you can see. Oh. Yeah, this is the relative pressure. And we have also the relative volume. Okay. So you can use either ones, the relative pressure or the relative volume, only when the process is isentropic. If it's not isentropic, then you don't use those two. We are using them now to get the H for the isentropic case, and then for the non-isentropic case, we can get it from the efficiency because he gave us the efficiency. Okay, so now we remember that our efficiency is 80%. It's equal to, we got H1 from the state that we have because we have the temperature, and then H2S, we can get it from the pressure, relative pressure relationships. How is that? We have the pressure relative for state 1, and then we can go see the problem. Was it this? I think this was it. Okay, so don't see the isentropic efficiency. the problem. Sorry for that. Okay. So we have the temperature, and from the temperature we can get the relative pressure 1, and we can arrange it in this way. This is the relative pressure 1 over the relative pressure 2 equal to pressure 1 over pressure 2. This is the interesting thing that we can use when we are having an isentropic process. And for the same thing goes for the relative volume relationships, okay? Relative volume 1 equal to volume 2 over volume 1. The same thing goes. But we are using pressure here because we do have the pressure ratios, pressure 1 and pressure 2. It's the amount of pressure raised by this compressor. So when this compressor operates, the compressor is going to increase the pressure of this stream of flow that we have. And because we have the increase in pressure of that stream of flow, then obviously we have the pressure ratios or the pressure rise in this compressor. So that's why we use the relative pressures, not the relative volumes, okay? Then we have the relative pressure at 1. We have pressure 1, pressure 2, but this one is the missing. You can get it. And now after you get it, go back to the tables. And then use the relative pressure that you got from the problem to get the temperature and the enthalpy. Okay, so this is what's interesting in this table. If you have only one properties of these, you can get the rest. Okay, so it's either that you know the relative pressure or the relative volume, but don't use them if you don't have an isentropic problem, only if you have an isentropic problem. And then you can get the temperature, the enthalpy, and everything else that it's asking you to do. Okay. Does anyone have any question? Okay, so the exit temperature of air, which is T2, and the required power input, that will be calculated from here. 80%, as I told you before. Okay, H2S, this is the one that we calculated from the isentropic process. And then H2A is unknown. Then H1. This is known, this is known, this is known, this is the only unknown. And then if you get this one, then you can know H2A minus H1 will be our actual work. If he asks you to calculate the work, then it's always the actual work case. So if he just says like calculate the exit temperature of the stream, so he means that I want the actual temperature of the stream at the exit. Or if he says like calculate the input work to the compressor, so he means the actual work, not the isentropic one. The isentropic one is going to be used along with the isentropic efficiency that measures the performance of the device to get the actual work. So you have the efficiency, okay, which is the performance of the device or a measure of the performance of the device. And you have a way from the tables to get the maximum performance of the device, the maximum performance cases. Okay, and when I'm telling you to calculate what do you have now, or what work can you consume, will you consume now, or what work you will produce now, so can be calculated relating those two to each other. Either you are going to have always the maximum performance will be in here down, but it's either for a power consuming device or a power producing device, then the actual and the isentropic are going to be flipped. That's it. But always when I'm telling you to calculate the work, or when the problem tells you to calculate the work, then you have to calculate the actual work. Okay, if it's just like saying work without anything else. So this is the only thing. For if you have a nozzle, then it goes by the same principle. The only difference that is you have velocities ratios, because remember in the nozzle device from chapter 5, okay, there's a nozzle device, the kinetic energy become important, especially at the outlet here, okay, because you are converging the flow to have a very high velocity here. When you reduce the diameter, then you are going to have a higher velocity, which will lead to a higher kinetic energies at the outlet. The pressure will drop in this case, but the kinetic energy will increase. So that's why you cannot ignore the kinetic energy in the nozzle. At the exit, look here, the actual kinetic energy at the exit and the isentropic kinetic energy at the exit, which is the maximum case or the ideal case of operation. Yeah, I think this talk about everything. The energy change of the system, in and out. You have the mechanisms of entropy. If you have heat transfer, then you are going to have Q over T. If you have work, then there is no entropy generated by work. And if you have mass flow, then it's going to be M times S, or M dot times S. And lastly, the entropy generated, okay, which is the coming from the irreversibilities. Now that we have discussed this one, lake and iron. Yeah. There are equations for determining the entropy for incompressible materials, such as water or solids or these stuff. Just look at them here. The equations of entropies for an isentropic process, it's going to be S equal to S, of course. And if you have an incompressible substance, such as water or solids, liquids and solids, then this is the change of entropy, okay? You don't have tables for these incompressible substances. Maybe water you have for, but other than that, you don't have tables or data. So you can use this equation, okay? It's an approximate one. And if you have gases, okay, then these are the two approximation equations, okay? And if you want to get the or capture the real effect that's happening, because these do not account for the change of the specific heat with relation to the temperature. Specific heats always increase or when we are increasing the temperature. So in these equations, we don't account for that difference in temperature that's going to change the specific heats. So here, this is a more exact treatment to the behavior that's happening there. Okay, it depends on the relative entropy here, which relates to the third law of thermodynamics, which translates to that in the zero state or at the 0 Kelvin, okay, state, we don't have any movement of the molecules of a perfectly crystalline material. Okay, there's a perfectly crystalline material. So its entropy is going to be exactly 0. Not the change in the entropy, but the randomness. The randomness of the molecules itself is going to be absolutely 0. Okay, because they are not moving, they cannot do anything at that state. Okay, but if the material is not perfectly crystalline one, maybe it's going to have some distortion. They are not moving, but the orientation is going to create some randomness from the orientation. That's going to make the entropy not zero, but very minimal. It's the minimum entropy that you can get. Okay, so this is the third law of thermodynamics. At the zero state, Kelvin, you have zero entropy for perfectly crystalline material and minimum entropy for other materials or non-perfectly crystalline materials. So this S note relates to the third law of thermodynamics in the sense that what is the entropy at the reference or at the zero state Kelvin, okay, for that gas. So you have some data for them, okay, you can look at them and substitute them here and then get the change in the entropy. Okay, so this is the meaning of the relative entropy. It's relative to the zero state. Okay, and that's pretty much sums the whole chapter. I know it's a long chapter, but like this is the time that we have. I think you are going to have a quiz in Exergy next week or the week after it. So I tried my best to cover everything for you that you have took in that chapter. And also to keep up with the quizzes schedule and this stuff. Okay. Last time we solved 2 problems in Exergy. I'm going to post for you the problems here in the because the time is over. I'm going to post for you the problems in the chat, and you can look in the problems, and if you don't understand the solution of them, the solution is already in the solution manual, you can get it. If you don't understand the solution, then you can refer to me by email, and other than that,
can you please share your email on the chat box, please?
Yeah, okay. Okay, let me see here. Contributions. The quiz will be next week, or when is the quiz?
Quiz will be on 15th. 15th.
On the 15th. So it's going to be Monday. Okay. For I think we have to solve at least 1 or 2 problems on the Exergy. Okay, for those of you who cannot continue, I will post the questions that I will solve. And for those who can continue with me, if you want, it's optional, of course. I'm going to solve 2 problems that involves the Exergy chapter in total, or everything related to the Exergy chapter. And then I'm going to post the problems here in the chat. So if you want, you can look at them. Okay. One of the interesting problems that I found is this one of dropping a hot iron block into water. Okay. So you have a 5 kilogram iron block initially at 350 Celsius and is quenched in an insulated tank, and that contains 100 kilogram of water at 30 Celsius. Assuming the water that vaporizes during the process condenses back in the tank and the surrounding are at 20 Celsius and 100 kilopascal. Determine the final equilibrium temperature, the exergy of the combined system at the initial and at the final states, and the wasted work potential during this process. So before we start with this problem, okay, there's something that relates the exergy destructed to the entropy generated, okay, which is this equation. Why is this term here? Because the exergy is a property of not only the system, but of the system and the environment combination, okay? Because if you are at the dead state, which is the state of the environment, then you cannot produce work. Because if you want to produce maybe work from heat transfer, you have to have different temperatures. And if you have a flow, you have to have different pressures. So if you are at the state of the environment, then you cannot produce work. We call it the dead state, okay? So the exergy is related to the environment. what environment do you have and what are the properties of your system are going to define the Exergy state that you have. Not only the system, like in the entropy or in the energy, you have also to look at the environment. So it's a combination or a combined property of the system and the environment, okay? So this is where this T naught is coming from. It's the temperature of the environment or of the surrounding. But the concept is the same, so that's why they are equal. The Exergy that's destroyed, that's coming from the irreversibilities, is equal to the entropy that's generated, which coming from the irreversibilities. So that's why they are equal, but there's this additional term that relates to having this entropy generate, to having the environment embedded with the system, okay? And also another thing that the Exergy coming from work is not zero, okay? Because Exergy is all about work, so how can the Exergy that's coming from work to be zero? And the Exergy that's coming from heat is equal to 1 minus temperature over temperature. I think the temperature of the boundary here and here temperature of the system. There is an equation for it, times Q, and the Exergy that's coming from the mass is equal to m dot x, okay, x small, and that's it. These are the only differences here between the Exergy balance and the entropy balance. Other than that, they are the same. So if you have a problem where you need to calculate the Exergy destroyed, you can maybe go to the entropy balance and then calculate the entropy generated and then multiply by T naught, and you have an easier approach to your problem. Okay, so we have this problem here. As we said, this iron block is have a temperature of 350 Celsius and it have a mass of 5 kilograms, and it was dropped in this water, which have a 30 degrees Celsius temperature and 100 kilograms of mass. So the first thing that he wants, the final equilibrium temperature. This should be easy. This is coming from the energy equation. And here another time we see the importance of connecting everything together. Energy in should be equal to the energy out in this case, okay? If we are dealing with each one as different systems. So if we want this one to be a system and this one to be a system, then the energy that was lost from the iron is going to the water. Or if you want to deal with them as a combined system that includes both here inside the chamber, then this is also possible. I will do it in this way. Okay, this is the iron block. So the change of energy of the system is equal to energy in minus energy out. And since both of these are zero, because this is my system, it's all about how you define your system. This is my system. So the change of energy in my system is going to be basically U2 minus U1. That's it, okay? Because it's a closed system, and then we have only internal energies equal to zero. So the internal energy for 2 should be equal to the internal energy at 1, okay? And then the internal energy at 2, okay, and at 1. This is a combination of the water with the rock. And this is also a combination of the water with the rock, okay? Because enthalpy and internal energy and entropy are all combined properties. We mean by combined properties that they do add. If our system is composed of several small systems, or let's say systems, several small individuals inside the system, then all of these small individuals can be added to form the total internal energy at that state, okay? So this is the internal energy of the rock, and this is the internal energy of the water, internal energy of the rock and internal energy of the water. We cannot calculate only the internal energy, just like the U1. We can calculate the difference. So I'm going to arrange it in this way. U2 of the water minus U2 of the rock is equal to U1 of the water minus U1 of the rock, okay? And then to put it in differences, we can take that one there and we can put this one here. So we'll have U2 of the water minus U1 of the water is going to be equal to U1 of the rock minus U2 of the rock. And then from here you can use that fundamental equation you got. If you have the internal energies, then you can use this CV delta T, okay? Or it's not like that, let me remember it. Yeah, MC delta T, okay. C delta T equal to MC delta T. Of course, here delta T is going to be reversed. 1 minus 2, here is 2 minus 1. And there is nothing CV or CP called because these are incompressible materials, okay? So the CP is equal to the CV is equal to C, just C, because they are incompressible materials, okay? We know the mass, we know the mass, we know the C, we know the C, and we want to calculate the final temperature. So here we put the final temperature. Here the initial temperature of the water is known, which is 30 degrees Celsius. It doesn't matter if you put Celsius or Kelvins here because it's a difference relation. And here we have the same thing, just that we have the initial temperature, which is 350 minus the final temperature that we need, okay? Just calculate the final temperature and it's going to be this, 31.7. Now for calculating the exergy of the combined system at the initial and the final states and the wasted work potential during this process, the exergy of the combined system is going to be the same steps that we did for the energy, except we are going to do it with exergy. So for the combined system at the initial and at the final state, so we want x2, which is equal to x2 of water plus x2 of iron or of the rock, and the same thing, so x1, which translates to x1 of water plus x1 of the rock, okay? In the exergy case, we can calculate the exergy for just x1 or x2 because we have the relation for the exergy is coupled with the environment. So when you say I want to calculate the exergy of the water at 2, so you are comparing the state at 2 with relation to the environment, O, okay? You know T naught and P naught. And here also you know T naught and P naught, okay? So just use the equation. I'm sorry I didn't introduce you to the equation, but it's nothing really. This is the equation of the exergy for a closed system. Of course, you have MC T minus T naught. So this is going to be T2 minus T naught. And this is T naught MC ln T minus T naught. Then you are going to find the exergy 2. And then you are going to find the exergy 2 of the water and of the rock. And then 1 again, comparing it with the environment. And this is how you solve part B. If you're going to solve part C, the wasted work potential, which is the exergy, nothing other than the exergy destroyed. So use that same principle. The change of the exergy of the system is going to be the exergy destroyed, because we don't have exergy in, we don't have exergy out. It's just this isolated system that deals, everything happens inside. We had x1 and x2 for everything, so just x2 minus x1 for water plus x2 minus x1 for the rock. Then you are going to put this here and you'll find the exergy destroyed, okay? This was my question, I think. So you see, like, doesn't require anything Just substitute and that's it. If you know like which term you are going to use, if you defined your system correctly from the first time, then there's nothing hard to do after that. Okay. So if we have a problem like this one, Exergy. Yes, so this one is for an open system. We have a refrigerant that enters an adiabatic compressor. So at this temperature and a saturated vapor rate of 0.45 meters cubed per minute and leaves at 900 kilopascals and 55 Celsius. Determine the power input to that compressor. So the power input to the compressor is going to be calculated from either the energy equation or the Exergy equation. But there's a problem. Do we have any heat transfer here in this problem? Okay, we have an inter-adiabatic compressor, saturated vapor, leaves that, so it doesn't tell us anything about if there is a heat transfer, and it's saying that we have an adiabatic compressor, so definitely there is no heat transfer there. Okay, and but we still don't know if we have some value of Exergy destruction or no, so we have to solve this part using the energy equation. Okay, because it says the power input to the compressor. And if you are solving with the Exergy equation, okay, then you are going to calculate the works or the useful works that you are going to extract. And you don't know if this power input to the compressor is the useful one or is there are some losses embedded in this power input. So you have to use the energy equation, the general one that does govern for anything. If you have losses, if you don't have the general case, and you solve for using the energy equation. You have the states. It's saturated vapor, 230 Celsius, and you have the flow rate, you have the leaving conditions. Just calculate the power input, okay? It's going to be H2 minus H1 times M dot. Then the isentropic efficiency, this is from the thermodynamics chapter. The isentropic efficiency of a compressor is going to be the work over the work, the work actual, because for a compressor, or the work isentropic over the work actual, because for a compressor, it's a work consuming device, and always the isentropic case is going to be taking or extracting less work. Okay, so we can we got this one already, the power input. And if we want to know the isentropic one, we have H1. Just do H2 as it was isentropic. Okay, so from here, take S1 and then put S1 or S2 to be equal to S1 and use your pressure. Okay, use the pressure. I know you have the pressure and the temperature, but you have to use the pressure. Okay. And after you use the pressure, then you are going to get the isentropic efficiency of that compressor. And then at last, you have the rate of the Exergy destruction from using this equation. Okay, you can either use this, the Exergy destructed is going to be equal to, you have Exergy in, which is going to be from the mass, okay, psi, minus Exergy out from the mass also, and it's going to be equal to the change of the system, which is going to be equal to 0 since we have an open system and we deal with the steady state systems. Or you can do it from the entropy equation, get the entropy generated. Okay, you don't need any work in the entropy balance equation, and then multiply by T naught, okay, to get the Exergy destructed. okay, or the rate of the Exergy destruction. And then finally, you need to calculate the second law efficiency of that compressor, which is a measurement of the performance also, but in relation of the Exergy and not the entropy. It's the same thing, just you are going to divide a work over work, but then it have like just different equations. So you are going to divide the Exergy that was expended over the Exergy that you are having for this system. Okay. Sorry that I went fast in this part, but I had to give you something for the quiz. I will post this for questions in the chat now. And as I said, if you have anything or any problem in the entropy, in the Exergy, or even in the thermodynamics chapter, then just email me and hopefully I will be available there. Thank you all and see you next time. Assalamu alaikum.